Choosing the right ceramic for tough mechanical jobs involves considering strength, toughness and hardness. These properties are distinct and can't be swapped out. Strength measures a material's ability to withstand loads, toughness looks at its resistance to cracks, and hardness focuses on resistance to scratching. Some ceramics that perform well in terms of strength, toughness and hardness include zirconia, the toughest and the strongest, silicon nitride, reasonably tough and strong, silicon carbide, hard and strong, and boron carbide, even harder. Alumina, while not excelling in any one property, is a reliable and cost-effective all-round choice. So keep in mind that the internal structure or microstructure of ceramics, including grain size and shape, can significantly affect their properties. Special techniques like transformation toughening or optimizing grain shape can enhance toughness and strength. It's essential to note that ceramics are much stronger in compression than in tension, so it's best to avoid tensile stresses wherever possible. Typically, ceramics are tested using a method called modulus of rupture, with both 3- and 4-point bending tests available, with the latter being more accurate. How do ceramics behave mechanically in fatigue or under permanent tensile loads? Ceramics generally don't fare well under tensile loads or fatigue conditions, so it's best to steer clear of these situations whenever possible. Unlike metals, ceramics can exhibit significant variability in strength due to defects like pores or cracks, even in supposedly identical samples from the same batch. Therefore, it's wise to over-design for both short-term and especially long-term loads or residual stresses. The Young's modulus, which measures stiffness, can be crucial for ceramic performance. Zirconia, for instance, has a low stiffness similar to steel, making it springy in thin sections, whilst alumina and other engineering ceramics are twice as stiff. Since batches of ceramics can have varying strengths, minimizing defects through specific processing methods like isopressing or hot isostatic pressing can help, although it may increase manufacturing costs. Smaller grain sizes can also boost strength. How do temperature or the environment affect the mechanical properties? In general, most ceramic materials exhibit lower strengths at higher temperatures due to the softening of any glassy grain boundary phase they may contain. However, this decrease is not linear, and there's usually an upper use temperature below which the material is considered safe for applications. Some ceramics, like zirconia, can be sensitive to moisture, which can accelerate crack growth. However, manufacturers are typically well equipped to prevent this issue. Radiation can be a concern in specific applications such as nuclear reactors or space environments, and different ceramic types have varying abilities to handle it, so expert advice may be necessary. Does the ceramic production route or component design affect the mechanical properties? The manufacturing process used significantly influences the final properties of ceramics because it affects the material's microstructure and the presence of defects. Wet or soft processing methods like slip casting, injection molding or 3D printing tend to generate more defects compared to dry, powder-based approaches. The shape, size and design of ceramic components also play a vital role in their properties. Sharp edges, tight corners and thin sections can act as crack initiators and should generally be avoided. When avoiding them isn't possible, incorporating 0.2 to 0.5mm edge chamfers or maximising radii can help. Smaller and rounder parts generally exhibit greater strength.